Hi, I'm Zor. Welcome to Unizor Education. So, this lecture is the third, actually, which is dedicated to Noether Theorem, and today I'm going just to basically prove it. The two previous lectures were about understanding what we are dealing with and certain mathematical models, and it's kind of a preparation, if you wish, for today's lecture. And today it will be just a mathematical proof, nothing more than that. So this lecture is part of the course called, in a course called Physics Plus, which is introduced on Unizor.com. The whole website, Unizor.com, contains other courses like Math for Teens, Math Plus, Physics for Teens, and this is a Physics Plus course. There is a relativity course, etc. So everything on the website is totally free. No advertisement, sign-in is optional. What else? Every lecture has textual notes, and these notes are basically like a textbook, and I recommend you before or after each lecture, wherever you found it, you might actually find it on YouTube or somewhere else, go to unizor.com and try to find this lecture on that website. And just on the same screen you have a lecture and you have the notes, the textual part, which is, as I was saying, just like a textbook, basically. Alright, so Noether Theorem. So there are certain things which I have already covered in the previous lecture, and briefly it's the following. First of all, we have extended configuration space, which contains time and all the space parameters. Now these are generalized coordinates. This is time. So we need time to geometrically, in n+1 dimensional space, represent the motion, not just the trajectory. Trajectory is where the particular object is moving, but it does not reflect how it's moving. With the time parameter, it goes to one more dimension, and the whole movement is a curve in that extended configuration space. So the motion is, really motion, all the details of the motion is represented in this extended configuration space as a curve. Okay, now, if it's a curve in a certain configuration space, then it can be mathematically described. Now, how the curves are described in mathematics? Using the parameters, parametrically. So you have certain parameter x, which belongs to some segment from A to B, real numbers, and basically all the coordinates are functions of this parameter. So if we are talking about a physical object which moves from point C1, Q1 to point C2, Q2, basically we can say that T1 is T of A and T2 is T of B, and correspondingly Q1 is Q of A and Q2 is Q of B, the beginning and the end of these curves. Okay, fine, so let it be. So we know about geometrical representation of motion. Again, not just the trajectory in the regular configuration space, but the motion in extended configuration space. Okay, so it's parameterized curve. Next we have, now this is a physical object, and it has Lagrangian. And Q prime. Now the letter Q represents actually q1, q2, q3, etc., qn, and the prime usually is a representation of time derivative. So this can be actually done as this way. This is t of x, q of x. Now the derivative of q by time can be represented as dq by dx divided by dt by dx. Since t and q are functions of parameter x, which x is from a to b, then the derivative of q by t, this one, dq by dt, can be represented this way. So everything is as functions of x. That's very important. So we have parameterized not only the coordinates, but also the Lagrangian as well. So everything depends on this parameter. It's very important, and it simplifies the whole thing. And I'll explain why. Now, next, after Lagrangian, we have action functional, right? So the action functional is actually defined as integral from t1 to t2. This is the beginning, time of beginning and time of the end of the motion. Lagrangian of t, q, and q prime dt. Now, this is really kind of not good. Why is it not good? Because everything depends on all the different parameters, parameter t and parameter q. Now, everything is parameterized by x. So I would like actually to reduce everything to x, to integration by x. That would be much easier whenever I will introduce transformation. Now, you know that motion, which is the physical process, can be modeled as transformation of coordinates. We talked about this in previous lectures. So the transformation of coordinates, we're talking about actually epsilon transformation. Where epsilon again is a parameter. It's not just one transformation. It's transformation by, well, you can say that in case we are transforming only time, then epsilon is interval of time we are transforming. If we are transforming only along one particular space coordinates, like q fix, then epsilon can represent basically the segment by which we are transforming this particular coordinate. Or in general, epsilon transformation, basically it's a transformation which is parameterized by epsilon, and with epsilon equal to 0, it's an identity transformation, which means does not really move the system at all. And it's supposed to be substantially smooth. I mean, it should be differentiable by epsilon. So we are moving a little bit. Epsilon, if epsilon is infinitesimal, then the transformation is infinitesimal in time and space. Okay. So whenever we will introduce this, our integration, limits of integration will also change. And to differentiate this in any way would be actually kind of a problem. So instead of this, we will just change everything back to x. Now, what is t1? T1 is whenever our parameter x is a, t2 is b. Now L will be, okay, so it's t of x, q of x. Now q, the differentiation by time, as we know, can be expressed in this way: dq by dx divided by dt by dx. And dt again is dt by dx and dx here. So this is under integral by x. So that's what's very important. We're just replacing one variable of integration with another. Instead of integrating by t, which is basically a function of x, we are integrating by x, which gives me exactly the same thing. Now, if I if I apply epsilon transformation, I apply it to t, I apply it to q, etc., to these functions, but my limits are fixed. So it's much easier to differentiate whenever I want to differentiate. So these are all assumptions which we are dealing with, all the kind of entities, items. So we have Lagrangian, we have action functional, and at this particular point, what is important is I would like to treat my time and space parameters on the same level, like symmetrically, in the same way, basically, because right now they don't look symmetrical. So instead of using this function Lagrangian, I will use a different function. I will use function L, which basically depends on time, time by dx. I'll use subscription x as a differentiation just to shorten the notation. Q and qx. This is differentiation by x, which is equal to L of t q dq by dx divided by dt by dx times dt by dx. This one. And now my integral looks like integral of a of b, L of t, tx, q, and qx dx. I mean, it looks much more symmetrical. My space coordinates are not different from my time coordinate. I will go even further. If I don't want to differentiate between them, what I will do is my time, I will just change the symbolics. My first q coordinate would be y1, my second would be y2, etc., and qn would be yn. Now, with this particular symbolics, my thing, instead of t and tx and q and qx, I can actually replace it with y and yx. Because now y is a group parameter, which means y0, y1, y2, y3, etc., which is all these, and this is the group parameter, which represents exactly that. So everything seems to be now back to my very, very simple action functional. I just changed symbolics, but now it looks like something which is relatively familiar with. So this is also the same action functional. Now, let's apply epsilon transformation. Now, this is the most important assumption which actually Emily Noether introduced, suggested that if we assume that action functional is invariant relative to epsilon transformation, that's an assumption. This is like given. If my action functional is invariant relative to epsilon transformation, then something must be conserved during this transformation. Now, epsilon transformation is a transformation by epsilon of any point. So for any point y in the extended configuration space, we apply epsilon transformation, and y goes to y epsilon, whatever the y epsilon is. Now, correspondingly, my pseudo-functional with this nice letter L will also change. And obviously, this transformation, which transforms point to point, point y to point y epsilon transforms the whole curve in the extended configuration space. So the curve will have basically all the coordinates will be transformed. However, it's still physically admissible trajectory. It's the same trajectory. So I'm just changing the coordinates, which means I'm changing the, well, if there is a numerical value for each coordinate, it's changing. But it's physically the same curve, and geometrically it's the same curve. Okay, so how do we mathematically express invariance of f, of action functional? Well, very simply. d by d epsilon of f is equal to 0, and I will put it at point epsilon is equal to 0. Now, obviously, function f now is dependent on epsilon. So function f of epsilon means epsilon here and epsilon here. So these are new values. Limits of integration are the same, that's very important. But under integral, these things are changing from y to y epsilon, and that changes the action functional. But if I'm saying it's invariant to epsilon transformation, then it should be constant, and its derivative by epsilon at epsilon is equal to 0 is equal to 0, the whole derivative. I mean, I probably should say it differently, I'm sorry. This should be equal to 0, like this. So now, why I put epsilon equal to 0? Well, we are talking about any point. So at any point, if we start with speed of changing of action functional to be equal to 0, it means it will be constant all the time, because we are talking about this thing to be true for every point, for every trajectory. I mean, this is actually depends on the whole trajectory, on the curve. So for any curve, for any physically admissible curve, that's supposed to be true. And again, the fact that I'm transforming something doesn't really change the curve itself, it just changes the numerical values. And from these numerical values, we calculate new value of action functional, and that's why action functional becomes a function of epsilon, but it's constant. It changes the coordinates of all the points on this curve, but the curve is the same and action functional is the same. That's what this basically means. So all I have to do right now is use this and see what happens. So the whole theorem is assume this and let's see what happens, and we will prove that something remains constant. Okay, so that's my purpose. All right. So first of all, I will probably skip epsilon is equal to 0. I will assume it's everywhere. And this is d by d epsilon of integral from a to b, nice L from y and yx dx. Now the x is a parameter from a to b, so x has nothing to do with epsilon. Epsilon is affecting only coordinates y and y and derivative from y to by x. So this is given that this is equal to 0. All right. So my first is I can interchange integration by x and differentiation by epsilon. So there is no problem with this. Again, with all the nice smooth functions, I can always do this. Okay, so that's my first. Again, with smooth functions, I assume everything is sufficient to make this type of. There are obviously some mathematical theorems when it's allowed, when it's not allowed. It's allowed. So whatever is necessary for those theorems to be allowed is assumed to be true. Now this is obviously these are functions of epsilon. Okay, so now I will have to differentiate by epsilon this particular function L. It's kind of made of Lagrangian times, well, let me just put it here, just in case we are forget what it is. It's Lagrangian of T Q Tx Qx times Tx, where subscription means differentiation. Here it's also differentiation by x. Okay. All right, fine. So how can we do this full derivative of a function of multiple arguments? Well, that's simple. So this 0 is equal to, we have to do partial derivative of L by the first argument, which is y, times dy epsilon by d epsilon plus partial derivative by the second argument times dy x epsilon by d epsilon. Okay, now, before going any further, I would like to talk about this particular thing. What is this? It's differentiation by epsilon of yx. Now, what is yx? We have just talked about it. It's a differentiation by x. So it's dy epsilon by dx. Now, so y depends on two parameters. X geometrically, because x is a parameter in this curve in n+1 dimensional space, extended configuration space, and epsilon is a parameter of transformation. So it's basically y is a function of two parameters, x and epsilon, and we're differentiating by them. So, I mean, if you have a function of two parameters, f of u and v, and you differentiation by let's say by u, and then differentiation by v. Well, in very, very broad number of cases, we can interchange differentiation by one and then by another. Again, there are mathematical theorems, but with the smooth functions, it's all fine. So I'll do the same thing. In as much as I change differentiation and integration, the order, I can change the order here. So that would be d by dx of dy epsilon by d epsilon. Okay? And now I will introduce, again, it's just a different symbolics. This thing, and if you remember, I omit epsilon is equal to 0. I assume that everywhere, wherever I have this differentiation by epsilon, I mean at point epsilon is equal to 0. So I will just introduce another variable for this. I will use zeta. Now, zeta is basically a speed of change, of transformation of particular coordinate. This is not just y, it's y1, y2, y3, etc. So these are group arguments. So this is kind of, so zeta is a speed of change, speed of transformation of any particular coordinate. It's just easier to carry it this way. And now, using subscription as symbolics for differentiation, I use this. So what does it mean? Well, it means that my integral, this one, is equal to integral from a to b of this particular. So it would be dl by dy times, now this thing I have defined as zeta plus dl by dyx by zeta by x dx. That's my integral. So nothing to it. So what I did, basically, I changed the differentiation by y and integration. That's one thing. And in this particular case, I change differentiation by x and by epsilon. That's it. Two differentiations were changed order. And just introduce the symbolic for speed of change, speed of transformation of particular coordinate. Again, zeta is also a group variable. Y is y1, y2, y3, and zeta is by 1, zeta1, zeta2, and zeta3. So this is actually a sigma, if you wish, of dl by dyi zeta I. And this is also an analogous sigma. It's easier not to carry it and just assume it's very easy this way. So, what does it mean? What do I have right now? Okay, one more transformation. I don't like this thing. I don't like zeta x. That's actually like one is the derivative by epsilon. This is the zeta, and then a derivative again. Too many derivatives. What I will do, I will use integration by parts to change this into something simpler. Okay. So what it is? What if I have dl by dy yx times zeta, just zeta, and I will differentiate it by x. What happens? Well, this is the product, so it's one times differentiation of another plus differentiation of this by this, right? So this is dl by dyx times derivative of zeta, which is zeta x, plus differentiation of this d by dx dl by dyx times zeta, right? So this I will represent as a difference between this and this. Now, first we do integration, because we need the integral. This is integral, right? From a to b. Now, this is by dx, obviously. dx and dx. Now, this is a full derivative of this times gx and integral. What is this? Well, this is basically, we already did this integral from a to b. Integral of derivative is whatever we are differentiating, right? This is a full derivative and integration. And this is equal to, now, and this now I will do it differently. I will put minus this one, minus d by dx dl by dyx times zeta integral from a to b dx equals this, which is integral from a to b dl by dyx times zeta x dx, which is this piece. So I would like to substitute this instead of this. So what happens? Okay, I can type out this. So this thing is equal to integral from a to b dl by dy zeta plus this one. So let me do first minus d by dx dl by dyx zeta plus this one dl by dyx oh, I think I forgot zeta piece here, times zeta from a to b. Almost done. I would like you to recognize something here. This. Let me rewrite it. dl dy minus d by dx dl by dyx zeta. I put zeta outside of the parentheses. Now this is Euler-Lagrange expression and equation, basically, which tells me that this is equal to 0. Y is equal to 0. We are on a physical trajectory. Since we are on a physical trajectory, the Euler-Lagrange equation is held because action functionality is the same, which means stationary points, stationary trajectories are the same whenever I'm transforming coordinates. And since every trajectory is a stationary point and satisfies Euler-Lagrange equation, then this Euler-Lagrange equation is satisfied in this particular case. So this expression is equal to 0 on any physically admissible trajectory for our system, and transformation which preserves the action function of the assumption we did in the very beginning. That's the key. We assume that action functional is invariant, and that's what makes Euler-Lagrange equation for any real physical trajectory to be equal to 0. So, which means that the whole thing, now we started from the whole thing which is equal to 0, right? This is differentiation, result of differentiation of action functional by epsilon, and we assume this is 0. So this is 0. Which means what? Which means that this expression at point A and point B are the same. Now, on any trajectory, we can choose 2 points arbitrarily and basically go from one to another. So A and B can be any points on any physical trajectory, and the difference of value will be 0, which means that the whole thing, dl by dyx times zeta, is constant. And this is the main result of Emily Noether. This is the Noether theorem. This is a quantity which is preserved. Now, what is this quantity? We will talk about next lecture. So, this is the law of conservation, which we have derived from invariance of the action functional to under the any smooth epsilon transformation. So next time we will talk about the meaning, physical meaning of this thing, what kind of conservation laws follow from it. But right now we have derived a general conservation law of something. We don't know yet what this actually is, but this is something which is conserved. Read the notes for this lecture. On Unizor.com you go to Physics Plus and Noether Theorem, Derivation. That would be a very nice technical, like a textbook basically. That's it for today. Thank you very much and good luck.